Where did we come from? It's a question that has haunted humanity since we first looked up at the stars. We've searched for answers in religion, philosophy, and science, but what if our origins lay beyond our pale blue dot? This is the radical idea proposed by the Panspermia theory. Life might have hitched a ride across the cosmos to seed our planet. The Panspermia theory suggests that we might be the descendants of extraterrestrial microbes. These microscopic travelers, carrying the blueprint of life, could have journeyed across unimaginable distances, tucked away on celestial vehicles like meteorites or comets. It's a concept that sounds like something straight out of science fiction, yet it has captivated scientists and philosophers for centuries. The idea itself is not new. The Greek philosopher Anaxagoras first proposed a version of Panspermia in the 5th century BC. He believed that life existed throughout the universe and was carried to Earth. Of course, back then it was just a philosophical musing, a thought experiment in a time before telescopes and microscopes. But in the centuries that followed, as our scientific tools and understanding of the cosmos evolved, the idea of panspermia began to take on a new life of its own. It moved from the realm of philosophy to the realm of scientific inquiry, a testament to the power of human curiosity and our relentless pursuit of knowledge. Imagine, if you will, a massive star nearing the end of its life. It explodes in a supernova, a cosmic cataclysm of unimaginable power. This explosion doesn't just obliterate, it creates, scattering the building blocks of life, like amino acids and nucleic acids. Out into the vastness of space, these organic molecules, essential for life as we know it, become interstellar travelers, drifting through the cosmos on dust grains and meteoroids. Their journey might last for millions, even billions of years, traversing the immense gulf between stars and galaxies. Some of these cosmic wanderers, carrying the potential for life, might eventually encounter a young habitable planet, a planet like the early Earth. Upon impact, these interstellar voyages could then potentially sow the seeds of life on this new world. Now you might be thinking, space is a pretty harsh place. How could anything, let alone life, survive a journey across the cosmos? The vacuum of space is unforgiving, but life is incredibly resilient. Extremophiles thrive in deadly conditions. They exist in boiling water, icy glaciers, and acidic mines. Life can exist in impossible environments. Microbial spores could survive space travel. Picture this: a comet, a celestial snowball of ice and dust hurtling through space. Embedded within its frozen heart are these microscopic travelers carrying the potential for life. Comets are like cosmic delivery trucks, ferrying material from the outer reaches of a solar system to its inner planets. As the comet approaches a star, it begins to warm up. The ice sublimates, turning directly into gas and creating that characteristic cometary tail we see streaking across the night sky. This process releases the dormant microbes, freeing them from their icy prison. Now imagine this comet on a collision course with a young, lifeless planet, the early Earth. The impact would be catastrophic, no doubt, but it could also be the spark that ignites the flame of life. The microbes, carrying the basic building blocks of life, would be deposited on this new world, ready to begin the long, slow process of evolution. We often think of life as being fragile, easily extinguished. And while it's true that many forms of life are delicate, life itself is incredibly persistent. It has an uncanny ability to adapt and thrive in the most unexpected of places. Consider the tardigrade, a microscopic creature often called a water bear. These little guys are practically indestructible. They can survive being frozen, boiled, exposed to the vacuum of space, and even blasted with radiation. If a tardigrade can survive all that, it makes you wonder what else might be out there, clinging to the surface of a comet or buried deep within a meteorite. Perhaps life in some form is far more common in the universe than we ever imagined. Perhaps it's constantly being shuffled and dealt across the cosmos, seeding new worlds with its potential. So far, we've been talking about the possibility of life hitching a ride on comets and meteorites. But what about evidence? Is there anything to suggest that the building blocks of life truly exist out there in the vastness of space? Well, it turns out that scientists have found some pretty compelling clues. They've discovered organic molecules, the essential ingredients for life as we know it, floating in interstellar clouds, those giant reservoirs of gas and dust scattered throughout galaxies. We're not just talking about simple molecules here. We're talking about amino acids, the building blocks of proteins, and even nucleic acids, the components of DNA and RNA. These are the very molecules that carry the genetic information for life on Earth. Now, finding these molecules in space doesn't definitively prove that life originated elsewhere and was transported to Earth. But it does lend credence to the idea that the ingredients for life are readily available throughout the universe, not just here on our little planet. One of the most compelling pieces of evidence for panspermia came in 1969 when a meteorite blazed across the sky over Murchison, Australia. This wasn't just any meteorite. It was a carbonaceous chondrite, a type of meteorite rich in organic compounds. When scientists analyzed the Murchison meteorite, they were astonished by what they found. It contained over 70 different amino acids, many of which are not found in life on Earth. It was like finding a cosmic cookbook filled with recipes for alien life forms. The Murchison meteorite provided the first concrete evidence that the building blocks of life could indeed survive a journey through space and land on Earth. It opened our eyes to the possibility that life's ingredients might be raining down on us all the time, carried on the backs of these celestial messengers. Imagine the implications. If a single meteorite could carry such a diverse array of organic molecules, what else might be out there, hidden within the countless celestial objects hurtling through the cosmos? The discovery of amino acids and nucleic acids in space and in meteorites is remarkable. But the panspermia theory doesn't just rely on finding these basic building blocks. It also hinges on the possibility that these molecules could somehow assemble themselves into more complex structures like proteins and DNA, the cornerstones of life as we know it. Now, the odds of these molecules randomly bumping into each other and forming complex structures in the vastness of space might seem astronomically small. And you'd be right if space were just a giant empty vacuum. But space isn't just an empty void. It's teeming with interstellar dust grains, tiny particles coated in ice and other molecules. These dust grains could act as microscopic laboratories, providing surfaces for organic molecules to stick to and interact with each other over millions of years, driven by the forces of gravity, radiation, and heat from nearby stars. These molecules could undergo a cosmic dance, forming increasingly complex structures, paving the way for the emergence of life's precursors. The Panspermia theory, if true, has profound implications. It suggests that life may not be a unique phenomenon confined to Earth. Instead, it could be a common occurrence throughout the universe, scattered across the cosmos like seeds on the wind. Imagine for a moment a universe where life is constantly being exchanged between planets, star systems, and even galaxies. A universe where life finds a way to take root and flourish in the most unexpected of places, carried on the backs of comets, asteroids, and interstellar dust grains. This cosmic interconnectedness, this grand exchange of life, paints a picture of a universe far more wondrous and awe-inspiring than we ever imagined. It suggests that we are not alone, that somewhere out there, amidst the trillions of stars and planets, other life forms may be looking up at the night sky, pondering the same cosmic questions that we are. If panspermia is correct, and life on Earth did originate elsewhere, it dramatically shifts our perspective on our place in the universe. Earth is no longer the sole cradle of life, but rather one stop on a much grander cosmic journey. It's like discovering that your family history extends far beyond the borders of your hometown, reaching back generations and spanning continents. Our true origins, in this light, might lie on a planet circling a distant star, a world we may never know. Yet, we carry a piece of that world within us, encoded in our very DNA. We are, in a sense, living proof of life's ability to transcend unimaginable distances and take root in new environments. This realization fosters a profound sense of connection, not only to life on Earth, but to the universe itself. It reminds us that we are part of something much bigger than ourselves, a cosmic story that began billions of years ago and continues to unfold today. The possibility of panspermia also raises the intriguing question: if life on Earth originated elsewhere, could there be other planets out there, seeded by the same celestial event? Could there be distant cousins of life, sharing a common ancestor with us, evolving on worlds we have yet to discover? Imagine the possibility of encountering these cosmic relatives, of comparing notes on the grand experiment of life. What would their biochemistry be like? Would they resemble the familiar forms of life on Earth? Or would they be something utterly alien and beyond our wildest imaginations? The search for extraterrestrial life takes on a whole new meaning in the context of panspermia. It's no longer just about finding life beyond Earth, but about connecting with our cosmic kin, understanding the full scope and diversity of life that the universe has to offer. The panspermia theory, while still a hypothesis, compels us to look at ourselves differently. If we are indeed the product of extraterrestrial origins, it challenges our anthropocentric view of the universe. We are no longer the sole proprietors of life, but simply one expression of a much larger phenomenon. This realization has profound philosophical implications, prompting us to reconsider our place in the grand scheme of things. Are there other intelligent civilizations out there also pondering their cosmic origins? Have they too looked up at the night sky and wondered if they are alone? These questions, once relegated to the realm of science fiction, become tantalizing possibilities in a universe governed by panspermia. The panspermia hypothesis, even if it turns out to be incorrect, serves as a powerful reminder of the vastness and mystery of the universe. It encourages us to think outside the box, to challenge our assumptions, and to embrace the unknown. The search for our origins is far from over. It requires us to delve deeper into the cosmos, to study distant stars and planets, to analyze meteorites and comets, and to continue pushing the boundaries of scientific inquiry. The answer to the question, are we aliens, may remain elusive for generations to come. But the journey itself, the pursuit of knowledge and understanding, is what makes us human. It is a testament to our insatiable curiosity, our desire to unravel the mysteries of the universe, and our place within its grand, ever-unfolding story. We've journeyed far, from the familiar comforts of Earth to the vast expanse of the cosmos, all in pursuit of an answer to a question as old as humanity itself. Where did we come from? The panspermia theory suggests that life might not be confined to our pale blue dot. It proposes a universe where life can be carried across unimaginable distances, hitching rides on celestial objects, surviving the harsh conditions of space, and eventually finding its way to new worlds. It's a grand and unifying concept, reminding us that we are children of the stars. The beauty of the panspermia theory lies in its potential to explain the origins of life on Earth and its profound implications for our understanding of life itself. If life on Earth originated from elsewhere in the universe, it suggests we share a common cosmic ancestry. The building blocks of our DNA could be scattered across the cosmos, echoing within organisms on distant planets. The diversity of life on Earth is just a glimpse of life's creativity throughout the universe. While the panspermia theory provides a compelling narrative for the origins of life on Earth, it's still a hypothesis. The pursuit of knowledge is a journey without a final destination. Each discovery brings us closer to understanding our place in the universe. The search for our cosmic origins will continue to drive us to explore space. Whether we prove or disprove panspermia, the true value lies in the questions it compels us to ask. For in the end, the quest to understand our origins is really a quest to understand ourselves.